A purse at radius 2 meters and a wallet at radius 3 meters travel in uniform circular motion on the floor of a merry-go-round as the ride turns. They're on the same radial line. A radial line is a line along the radius, so it looks like this. I have a purse located 2 meters from the center, say there for example, and I have a wallet located 3 meters from the center, say there for example. I'm going to redraw this merry-go-round from a top-down view. That's my merry-go-round. Here's my radius line. Here's my purse, and here is my wallet. The problem says at one instant the acceleration of the purse is 2 meters per second squared I hat, so let me draw that. This is 2 meters per second squared in the I hat direction. And the purse also has a y acceleration of 4 meters per second squared j hat. That looks like this. Centripetal acceleration means center-seeking acceleration. If an object like this purse or wallet or the moon, for example, is moving in a circle at a constant speed, it's constantly accelerating towards the center of that circle. The magnitude of this centripetal acceleration is a subscript c equals v squared over r. V stands for velocity, and in this case it means tangential velocity. Let's say this merry-go-round is spinning in this direction. That means the tangential velocity of the purse would look like this. It would be perpendicular to that radius line. The tangential velocity of the wallet would look like this, again, at a right angle to that radius line, and it would actually be longer. This is a longer vector because the tangential velocity is greater as you go further away from the center. In this equation, a subscript c equals v squared over r. The r stands for the radius of the circle, which looks like this. Let me redraw things here so it's easier to look at. I'm just showing the purse and the wallet and the radius line. If I add these two centripetal acceleration vector components, I get this net centripetal acceleration for the purse. I'm going to move this a sub y vector from where it was to this position so I have it lined up with my ax vector. I can do that as long as I don't change the direction or the magnitude. I can move vectors all over the place. And I'm doing this because I want things to go from tail to head, from tail to head. Okay, so now I can just use the Pythagorean theorem to calculate the magnitude of a sub c for the purse. It's going to be the square root of ax squared plus ay squared, which equals the square root of 2 meters per second squared plus 4 meters per second squared, which equals the square root of 20 meters per second squared. Let's go back to equation number 1. A subscript c, centripetal acceleration, equals v squared over r. V is velocity, and I know velocity is distance over time, and I know the distance is just the circumference of that circle, 2 pi r. The time it takes to complete that distance is capital letter T, which stands for period. Period is the amount of time it takes an object to complete one cycle. So here's velocity. Now all I need to do is square it like you see me doing here. That's my numerator. Here's my denominator, r. And now I'm going to simplify it and use subscripts because I can't forget about my wallet. Once again, for the purse, this value equals the square root of 20 meters per second squared. Okay, for the centripetal acceleration of my wallet, I have a sub c equals v squared over r once again. And once again, velocity is distance over time. Distance is just the circumference, and time is the period. That's my numerator, squared, divided by r again. And when I simplify and add subscripts to make sure I remember I'm working on the wallet now, I get this. If I look at these two values, tw, the period of the wallet, and the period of the purse, t subscript p, I can see that they're equal. I'm just going to call it t. They're equal because the amount of time it takes for this purse to complete one cycle is the same amount of time it takes this wallet to complete one cycle. So for example, if it took the purse sitting on that merry-go-round 5 seconds to make one complete cycle, then the wallet, which is also sitting on that same merry-go-round, would also take 5 seconds to complete one cycle. The period of the purse equals the period of the wallet. Okay, I'm going back to equation number 1 and rewriting it like this. Right here, I'm going to rewrite equation number 3, which is the centripetal acceleration for the wallet. Okay, it's time for some algebra. I'm going to divide this top equation by the bottom equation. It's like, for example, if I had the equation 3x equals 12 and simultaneously the equation x squared equals 16. If I divide the top equation by the bottom equation, I would get 3 over x equals 12 over 16, or x equals 4. Same thinking. So when I divide that top blue equation by that bottom blue equation and simplify, here's what I get. Okay, I know my purse is sitting at 2 meters. R subscript P is 2 meters for my purse, and my wallet is sitting at a position of R subscript W of 3 meters. So now I can solve for the magnitude of my wallet's centripetal acceleration. Here it is. I'm going to add my wallet's centripetal acceleration on the same drawing here, and I'll also add the x and y components. This is the x component of my wallet's centripetal acceleration. I'll write it like that. This is ACWY, which I would read as the y component of my wallet's centripetal acceleration. So once again, this orange triangle is a right triangle. My hypotenuse is the centripetal acceleration of my wallet. And notice that I have similar triangles. That blue triangle is similar to that orange triangle. So from a similar triangle perspective, ACP is to ACW as 2 meters per second squared is to the x component of the wallet's centripetal acceleration. ACP is the square root of 20. ACW is 3/2 times the square root of 20. So from here, it's pretty easy to solve for ACWX, the x component of my wallet's centripetal acceleration. Using similar triangles again for the y component, as ACP is to ACW, so is 4 meters per second squared is to ACWY, the y component of my wallet's centripetal acceleration. Once again, I know ACP, I know ACW, I can solve and get ACWY equals 6 meters per second squared. This is the x component of my wallet's centripetal acceleration. This is the y component of my wallet's centripetal acceleration. And that's it. This problem does a good job reinforcing several elements associated with centripetal acceleration.